Okay, so we figured out how to look at a relationship and determine if it's an ellipse, hyperbola, or parabola. For example, here for this relationship we have a equals 1, b equals square root of 3, and c equals 2. Putting that into our little formula, b squared minus a squared times 4 minus 4ac, not a squared but ac, we end up with 3 minus 1 times 2 times 4. 3 minus 8 equals minus 5. So this is, of course, an ellipse. But it's not just an ellipse like we have plotted so far. It's a little different because this ellipse will end up being rotated. Actually, it'll have the 0, 0 as its origin. You can see here that's the case, but we will rotate this thing so it'll look something like this. This ellipse is going to end up looking something like this in a rotated fashion. So it won't. Its major and minor axes don't match up with the x and y axis. So in essence, this is like a new x-axis here, and it has been rotated by some angle theta. So the question is, what is that theta? How do we figure it out? Well, turns out the relationship we can use to determine that is the cotangent of twice that angle, 2 theta, equals a minus c over b. Quite simply, a minus c over b. And furthermore, you can see that if our ellipse was originally looking like a typical ellipse that like I've dotted here in red line, that we've gone through before, that I could rotate this any amount, and once I rotate 180 degrees, it'll just start repeating itself again. So really, in this problem, we don't have to concern ourselves with anything but 0 is less than or equal to 2 theta is less than or equal to 180 degrees. We don't need to concern ourselves with the full 360 degrees of the circle. That simplifies this process a little bit. But anyways, getting back to this equation, we can look here and insert these values. So we get 1 minus 2 over square root of 3, which equals minus 1 over square root of 3. So we could rewrite this, if we don't want the square root of 3 in the denominator, we could rewrite this as minus square root of 3 over 3. And if you study the unit circle, you'll see that this appears in one of two spots. Let me put where it appears somewhere around here, and it appears over here. Notice those corresponds with either side of the way this ellipse is going to end up looking. That isn't just a coincidence. But this lower value down here, we don't need to worry about. So only concerning ourselves with this up here, we'll determine then that the cosine, or the cotangent, the cotangent of 2 theta actually equals 120. Actually, 120 degrees equals theta. The cotangent of 2 theta, of course, was equal to the minus the square root of 3 over 3, which means that 2 theta equals 120 degrees. That then means that theta for our purposes equals 60 degrees. So as you can see, the x-axis here in our problem is this is going to actually be equal to 60 degrees. So our new axis is going to be 60 degrees offset from that axis. So where do we go from there? How do we figure out how to plot this thing? Well, we need to study and really define our new axes. So if this is the y-axis and this is the x-axis, then we're going to rotate to a new axis. We're going to rotate some angle theta. Of course, it's equal to 60 degrees, we've already determined, but I'm going to write this in a general sense. And the new axis we're going to call x prime. So if we have an x prime, 90 degrees from that is y prime. So now what we'll end up doing is we'll end up plotting our ellipses on this new axis once we figure out. And we'll have this angle, so we'll know exactly where it is. So the question is, what is, how do we come to terms with x prime and x, and how do we relate the two? So okay, so if we have a point here that is in our Cartesian axes, it's going to be the point xy, right? We'll come over some x value, go up some y value, get the point xy. But at the same time, we could look at this rotated axis, and it's going to be some value, I guess I'll do blue here, some value x prime, and then up some value y prime that is parallel to this new y prime axis. So it's also equal to the point x prime y prime. So how do we define what x prime y prime is? We can determine that by looking at this triangle. First, let's look at this triangle here, 90 degrees. So let me pull that off. So this is, now this red line here has a distance we'll call r. We'll say like the radius. We'll call r though. So this is a distance of r. This is 90 degrees. This would have been our x prime axis. This is our y prime axis, for example. So this is the y prime. So this point P of x prime y prime, which of course is also equal to P of xy, but this P of x prime y prime, there's going to be some angle here, alpha. So this is alpha. This is the angle off of the x prime axis to r. And so we can define this as we're going to have an x direction and a y direction for the x prime y prime. So the distance of x is, so our x prime distance, so that's like our x prime distance is really going to end up being, if you can think of x over r equals cosine of alpha, so x prime over r equals cosine of alpha, therefore x prime equals r times cosine of alpha. Well, likewise, we're going to have this y prime distance, and y prime is going to end up being r sine of alpha. And looks like we're about out of time. So I'll pick this up in the next video.